Hello and welcome to this webinar. My name is Sisiopiku and I'm a faculty at the University of Alabama, Birmingham. And I'm here with my colleague, Turochy from Auburn University to deliver today's webinar, the title of which is on the screen, and it is focusing on traffic parameters, merge configurations, and capacity modeling for freeway work zones. And in fact, this webinar is part of a STRIDE series of webinars and is sponsored by the STRIDE Center. And as many of you may already know, STRIDE is the 2016 USDOT Region 4 University Transportation Center. It is a consortium of 10 universities in the Southeast with the University of Florida as the lead institution. And our mission is to develop novel strategies for reducing traffic congestion. And in fact, in this webinar, we will talk about traffic congestion related to work zones. And the reason that this topic is important is that construction work for maintenance and rehabilitation is a very common occurrence on freeways and other transportation facilities. And as studies show, the probability of a driver to confront an active work zone is 1 out of every 100 miles driven on the highway, as about 20% of US national highway system roadways experience construction work during the peak season. When that happens, often we have lane closures and congestion develops as the capacity decreases. We can experience delays and drops in speeds for up to 32 to 56% compared to regular speeds. So these are areas that need attention. So to minimize the congestion impacts, we need to understand exactly the operations during the construction zone configurations and see how we can improve these configurations so that we have a smooth travel through work zones. So in this study, we examined several aspects of the modeling of freeway work zones, including how work zones with 3-to-1 lane drop configuration work and different types of temporary traffic control. We also looked at how field data from freeways with work zones can be used to evaluate default parameters in traffic simulation programs. For example, track acceleration capabilities and time headway distributions. And we also looked at how stochastic approaches can be used to determine the capacity of freeway lane closures in order to estimate the probability of breakdown and resultant queuing. I will talk more on the first of these 3 topics, and then Rod will give you some background information and findings from the other 2. So the first topic focused on assessing traffic control options for 3-to-1 lane closures. Motivation for this study was an earlier study that we had performed here at UAB that was also sponsored by STRIDE UTC, where we have asked Department of Transportation representatives to give us some information about how they choose the traffic control when they plan for work zones. And what we found from these responses was that most of the DOTs actually do not focus this decision on specific considerations related to operational or safety impacts, but rather their knowledge and prior experience. And mostly they choose early merge temporary traffic control. We also looked at the literature and found out that earlier simulation studies mostly considered short-term work zones during off-peak times, and most of the studies focused on 3 to 2 lane reductions. So there was very limited work done for 3 to 1 lane closures. And so we thought that this is a topic that needed some additional attention. With that in mind, we decided to investigate the operational impact of 2 types of static temporary traffic control for 3 to 1 work zones during peak as well as non-peak traffic conditions, and for a variety of work zone lengths. And our intention is to understand better how the different options work and provide some guidance regarding effective selection of temporary traffic control strategies in these types of lane closures. So our study site was an actual site of a segment of I-65 that goes through Birmingham, Alabama. The study area was a 12-mile long stretch. And we used this, the characteristics of this segment into a simulation model. We got specific data about traffic volumes from ALDOT, who collects such data on a routinely basis. And the data were from April 2018, and we used the typical weekday, Thursday, in order to obtain the information. And also we made a few assumptions, including an assumption of 10% traffic volume being track volume. So the experimental design is highlighted in that next slide. The base model that we simulated represented the 24-hour traffic demand. And then we developed scenario to look at work zone configurations. We had the 3 to 1 lane closure. That means the 3 lanes dropped to 1 lane, and we closed the two rightmost lanes, so the right lane and the middle lane, in all of our experiments. And we ran 18 different experiments representing a combination of traffic control strategy, work zone closure type, and length. So we considered 2 traffic control strategies, the early merge and the late merge, and I will give you a little background on each. 2 3 to 1 lane closure types, the long term and the short term. We both looked at the AM peak and non-peak for the short term, and then 3 work space lengths of 500, 1,000, and 1,500 feet. So this slide and the next describe the difference between the early merge control and the late merge control. So during the early merge control, which is a very typical type of control used here in Alabama, we encourage the drivers to merge to the open lanes early on, way upstream from where the lane drop will take place. While for the late merge, the drivers get very close to where the lane drop will happen, and then they are really encouraged or forced to shift to the open lanes. So it is a different configuration there. We developed the base model and all the work zone models using VISSIM, which is a very well-known and widely accepted micro simulation model for traffic simulation studies. And of course, we needed several entries there for detailed geometric characteristics as well as detailed traffic volumes. And VISSIM gives a lot of detailed MOEs, measures of effectiveness, and we considered flow density, travel time, and speed in our study. We put a lot of effort in calibrating and validating our base model. Because that way we can have confidence on the model being representative of the actual field conditions. In order to do this, we obtained data from NPMRDS, that's a national database, and this data were travel times data, and that are collected routinely. So we wanted to compare the field data with the simulated travel times resulting from the model. And we decided to accept a model that is within plus or minus 15% of, that gives us travel times within plus or minus 15% of the field data. So we had to adjust the different calibration parameters until we found a reasonable model. And this next slide shows you the validation result. So what you see with the dotted lines are these boundaries, plus or minus 15% from the field data that is shown here in mustardy in yellow, let's say, and then our actual travel times from the model that we constructed are shown here with the dark line, and you see that those are definitely within this range that we wanted them to be and very close to the actual field data. This, as well as this next slide, where we plotted the travel times from the simulation model against the actual travel times from the field data. And we put we fitted this line here that has an R-square of 0.90. Gives us a lot of confidence that our model represents well the actual conditions. So we used this model, and then we had to adjust it in order to introduce the work zone configurations. And sometimes this is easier said than done, because neither VISSIM nor any of the other models have any specific button for work zone configurations. So we had to work with the models in order to make it behave the way that is compatible with the early merge and the late merge behavior. So we used link structures and connectors along with root decisions in order to provide the scenarios for work zone, representing the work zone operation. As we worked with the simulation model, with something that is typical with this type of work, we had some warm-up time, 3,600 seconds for the 24-hour study and 900 seconds for the short-term lane closures. And we performed 5 iterations for each scenario. And we wanted to be able to compare apples with apples and oranges with oranges. So we used the same 5 random seeds as we generated the traffic flow and then averaged the data. And that's how the comparisons were performed later on. Speaking about the comparisons, let me take the next few minutes to discuss our results from the data analysis. First, we looked at long-term work zones where we had the lane closure implemented during the entire 24-hour of simulation. And we put the work zone length of 500 feet that was placed almost in the middle of our 12-mile corridor. And we looked at flow data or the volumes, and the results, as you can see on the screen, showed that in the very beginning, when we had very low traffic right after midnight and in the early hours, then, you know, we had no problems at all. But as the traffic started picking up around 6 a.m., then we noticed that the volume actually, I mean, the dropping the 2 lanes created a major issue. And we see here both the 3-to-1 early merge as well as the 3-to-1 late merge configuration. And we see that both of them were not able to achieve any good results. At the end, we can see that the system really failed to accommodate the traffic, and it remained congested for the duration of the experiment. What you see here is an actual reduction of flow of 56 to 60% for early merge and 55 to 58% with the late merge. And these same findings were confirmed as we looked at the other measures of effectiveness. Here is an example with the density analysis. The conclusion from this part of the work was that the system really could not handle a 2-lane, a closure of 2 lanes for that extended time period. And so it failed. So we thought that, okay, since the long-term work zone will not work with the 3-to-1 configuration, let's see what happens if we have short-term work zones. And we started with a worst case scenario for this, where we selected the AM peak. We modeled the northbound in these slides that you see. So that was the worst peak that we had. And here are the results from the flow analysis and the density analysis. And when we looked at this for a work zone length of 500 feet and compared the performance of early merge and late merge, we can see that the late merge performed a little worse than the late merge. And that was consistent for all the MOEs that we observed. Here again, you know, this is the performance without work zones and work zone in place. And this line represents the 3-to-1 late merge scenario. And then the green line, the 3-to-1 early merge. So from what we can compare here, we can tell that, you know, there is some slightly better performance of the late merge scenario. And this was, as I said, consistent with all the MOEs, and this is what how it looked when we looked at travel times and when we performed the speed analysis. Again, small differences, but always consistently the late merge performed a little better. So these results focused on 500 feet work zone. So for the AM, we looked also at 1,000 feet work zones and then 1,500 feet. And what we observed is as the length of the work zone increased, then it seemed that those slight benefits of the late merge were not, did not remain relevant. So we see that when we increase the length of the work zone, then the performance between the early merge and the late merge scenario were pretty much identical. And that was the case also with the 15,000 feet as well. So then we decided to explore how the results look like if we select the non-peak time period And we selected late night from 9 to end of 11 p.m. And the results are shown here. Once again, we can see a slightly better performance for the late merge. But those, and these are consistent throughout all the MOEs. For example, if you focus here on the speed analysis, again, you know, the speeds, of course, during the presence of the work zone are less than without, but pretty close. But those differences, we thought that were very close. And so from observation, we could not tell whether or not they were statistically significant. So we decided to do a little bit of statistical analysis, focusing on t-tests to determine if there is any statistically significant difference between the two temporary traffic control options that we considered. And the results are shown here. The t-score had to be more than 2.13 in order to ensure with 90% confidence that the MOEs are significantly different between early and late merge, and it was not the case. So what we found out from that part of the analysis is that although we observe some differences, they're not strong enough to make us believe that there is a huge advantage of using the one option versus the other. So the takeaway from this part of the study was that based on our simulation experiments, we confirmed that when we drop 2 lanes out of 3 for an extended period of time, then the network cannot function. So we have failure. And so we should consider short-term rather than long-term lane closures when we have the 3-to-1 scenario. And when we do and close the lanes during peak hour, then the late merge performs slightly better, but only if the work zone is very short. But during the non-peak hour, late merge performs slightly better than early merge throughout the different types of work zone lengths that we have, but still those differences are small and not statistically significant. So from all this, we recommend that long-term work zones are not scheduled for 3-to-1 lane closures unless traffic diversions are considered in order to move some of the traffic away from the affected area. And we did not consider any traffic diversions in this study just because we wanted to see the actual impact by the vehicles using the facility under that restricted scenario. And when we schedule short-term work zones, then as it is often the case for cases where we drop 2 lanes out of 3, it is best to schedule them during non-peak hours rather than peak hours. And there is a slight benefit of considering the late merge control. And we did find late merge control actually to work better for 3-to-2 lane drop configurations in other work that we have done that is outside the scope of this presentation. So with that, I would like to turn it over to Rod, who will present the results from the rest of the study. And in the meanwhile, I would like to invite you to contribute questions through the chat box if you have not been doing that already, and we will try to answer those questions at the end of the talk. So while I'm stopping my share of the slides, and so that Rod can put on his, I would like to thank the Stride, who was sponsor of this study, and Aldot as well. And also I would like to acknowledge Troy Saha, who was the graduate research assistant who contributed to this study as well. Thank you very much for your attention, and I think Rod is almost ready to take it away. Rod?
Okay, thank you, Virginia, for talking about the portion of the research that you all had worked on up there at UAB. I hope you all can see my screen. Let me go ahead and put my slides in PowerPoint viewer mode. So I guess at this point, we'll talk for a few minutes about the portion of this research project that was conducted at Auburn University. And thank you again, Virginia, for sort of setting the stage as to why this is important work and the impact that work zones have on the traveling public, as well as on the agencies that manage those facilities. We'll see in a minute, that was one of the ingredients that helped shape the work that we conducted here at Auburn. So on this cover slide, I've also listed Nick Jean. He was a graduate research assistant at Auburn a couple of years ago who actually did the bulk of the work that we're going to talk about. He's currently with Kimley Horn in Charleston, South Carolina, and I'm here at Auburn University still. So we'll go ahead and get started. Here's a list of the tasks as they were written in the research proposal. Rather than trying to read all those words, we'll just go ahead and simplify these in terms of the tasks that were conducted at Auburn. So once we got into the literature review and also had some discussions with the Alabama DOT to kind of get their interest as potential stakeholders in this research, we modified those tasks and objectives that we had on the screen a moment ago and ended up kind of setting these out as what we wanted to accomplish, was to collect data at a 2-to-1 freeway lane closure with traffic sensors that we deployed, and then develop and calibrate a traffic simulation model of that lane closure. And we used the simulation tool VISSIM that Virginia had mentioned earlier. And then we wanted to look at the suitability of some of the key default traffic simulation parameters that exist in VISSIM and take a look at their validity with the field data. So we'll elaborate on that as well. And then also kind of added the notion of exploring the feasibility of a probabilistic approach to capacity of a freeway lane closure. So in the next 15 minutes or so, we'll elaborate on all of these items that are the objectives that we ended up taking a look at. But essentially, based on literature review and conversations with the Alabama DOT, this is what we ended up setting up as our objectives. Oh, and also that this notion of looking at work zone freeway lane closure capacity stochastically or probabilistically rather than the traditional more deterministic approach, we also thought that this could help form the basis for a decision support tool that transportation agencies such as state DOTs could use to make more informed decisions about when it's an appropriate time to allow a contractor or their own forces to close a lane in terms of the traffic impacts from both a mobility as well as safety perspective. So we'll elaborate on all that in the next few minutes. So looking ahead here, here's an outline of the presentation for the next few minutes. It's divided in these 5 sections. We'll spend 2 to 3 minutes or so on each of them. We'll talk about the data that were collected and then processing, and then take a look at the traffic simulation model development and how it was calibrated, and then explore some of those default parameters in VISSIM and take a look at seeing if they need to be modified based on the traffic that we observed, and then kind of set the stage for taking a probabilistic approach to estimating the capacity available through a freeway lane closure, and then wrap that up with some conclusions and recommendations. So data collection and management first, of course. Here's a sort of schematic of the site. We collected data at a freeway lane closure on I-59 and 20. They overlapped through much of their journey in Alabama. So this is just southwest of the Tuscaloosa area, so sort of in the west central portion of the state, where traffic heading southbound first saw a couple of changeable message signs to let them know that they were approaching work zone, and then sort of the standard lane closure work zone signage. So this site has about 28,000 vehicles per day in both directions combined. So we can also see here in the figure to the right where we deployed our traffic sensors. We deployed them in 1 mile increments at a half mile ahead of the taper, 1.5, 2.5, and 3.5 miles, traffic moving from left to right. And then just downstream of the actual taper, once the 2 lanes of traffic had been merged into the single lane that was available as traffic passed the work activity site. So this again was southbound I-5920, just southwest of Tuscaloosa, Alabama, a 2-lane to 1-lane closure. We collected data for 14 days, and on day 6, the lanes were switched for this pavement repair project. So we were actually able to collect data for both a left lane closure and a right lane closure, and there are some differences between them, as we'll see here in a moment. So talking a little bit more about the data collection, we needed to, of course, exercise a little bit of quality control on those traffic data. So we screened the data, and one of the things that we screened the data for was appropriate or sort of acceptable, feasible values for vehicle length, because this is one of the items that was measured by our traffic sensors that were deployed. And we can see here on the right a figure showing the distribution of vehicle length from 2 different sensors that were 1 mile apart but in the same lane. And there are no interchanges or on-ramps or off-ramps throughout this entire section. So theoretically, it's all the same traffic across all of our sensors. And we can yet see with the blue representing one sensor and then the orange representing another sensor a mile upstream, that the distributions of vehicle length varied quite a bit, even though it should have been much the same traffic except for perhaps a few lane changes. So that's an indication that there's probably a need to assert a little bit of quality control on the data. So we took a look at the vehicle lengths across all 9 sensors and ultimately merged those and developed some practical as well as somewhat arbitrary thresholds to eliminate data that we felt might be erroneous. So for example, any vehicle lengths less than 5 feet, at that point you're shorter than a motorcycle. So that's actually data that can't really be believed to be accurate. So such vehicle lengths were removed. And then somewhat arbitrarily, vehicle lengths over 100 feet were also removed. We conducted some quality control on vehicle speeds as well with a similar type of logic process, and ended up deciding to move vehicle speeds less than 5 miles per hour and also greater than 90 miles per hour from further use in our research. So once that quality control was performed, we can see these speed distributions at the site. And this is typical of what we see in freeway traffic data in terms of that speeds do vary between the left lane and the right lane, and they also vary between passenger cars and trucks. That's why we have a total of 4 curves here. Moving from left to right, we have trucks in the right lane or the slow lane, that's sort of the faded blue. And then in the deeper blue, we have the passenger cars in the right lane. So we can see the speed distribution for faster cars differs a bit from the trucks. And then we have trucks in the left lane in the light green, and then passengers in the left lane in the deeper green. And again, the passenger car speed distribution is a little higher, a little faster than it is for trucks. And certainly the left lane is higher than the right lane. And that's all within, I think, what we would typically expect. Next, let's take a look at how we developed and calibrated our model. So it was important to identify breakdown conditions in terms of when did the operating lane closure reach capacity. Now, ultimately, based on the data from the traffic sensor, some sort of algorithm or decision rule set needs to be applied to declare that a breakdown actually existed. And the 6th edition of the Highway Capacity Manual, published about 5 years ago, provides this suggestion: is when average speeds remain more than 25% below free flow speed for at least a 15-minute interval. So at our site, within the lane closure itself, the most downstream sensor just beyond the taper, the average speed in free-flowing conditions was about 50 miles per hour. So we chose to use a threshold of 35 miles per hour, which is a 30% reduction from free-flow speeds. And if the speeds were sustained below 35 miles per hour for more than 15 minutes, then a declaration was made that a breakdown has occurred. Best we can tell from the traffic data. When we're talking about a breakdown, of course, that means that flow moves from stable to unstable and capacity, at least momentarily, has been reached. And at that point, queuing starts to form. And when queuing forms, moving upstream in traffic, that's when the mobility impacts, as well as the safety impacts for traffic really go up. And we can see here in this table, there's a lot of data here, but we looked at different types of breakdown flow rates. And we can see, for example, that the flow rates when the left lane is closed are a little bit lower across the board than they are when the right lane is closed. And again, that's kind of to be expected as well. And we can see that they are across a range. When we observed breakdown events in our 2 weeks worth of data, it wasn't always the exact same flow rate that precipitated the breakdown condition. It varied a bit. And that, again, goes toward the notion of looking at capacity in a freeway lane closure probabilistically rather than stochastically. So moving along through model development and calibration, here is a plot of traffic during a typical day during the data collection period, where it was early to mid-afternoon that the volumes or the demand were such that we had a breakdown addition occur, which that's again typical of a rural freeway. In the orange, we have the moving average for 15-minute intervals of speed, so that we can see that at about 2 o'clock p.m., speeds really started to drop and fell below the threshold shown in the dashed line of 35 miles per hour. And then speed stayed suppressed below that line for about 4 hours before the upstream demand had decreased enough that the queue could be cleared. And this is important because this was a target in our model calibration. Travel time is often used as a target value for or variable to use for calibrating the model. Mean speed is essentially another way to look at the same type of information, and that's what was used in our portion of the study. So for the folks who are really interested in the calibration parameters that were looked at, this is a little deeper dive here. These are the items that we looked at for conducting calibration, or key tools within the VISSIM software that were used. One is the desired speed decision tool to force speeds to replicate what's in the field. Our target was that the mean error in speed was less than 20% in terms of deviation from the actual field measured speed, comparing that with the speeds that were produced by the simulation models. And here also is a list of parameters within VISSIM that we explored based on, again, prior experience as well as what's in the literature in terms of typical parameters to manipulate the values for, to try to close the gap between what was observed in the simulation model and what was observed in the field. In other words, trying to get to an acceptable level of calibration. It's also worth noting that with our field data, we were able to actually measure time headway rather than just making some assumptions or using the default parameters in the model. So this again provided an opportunity for us to explore sort of the adequacy of just using the default values that are provided within the general traffic simulation software. So let's take a little closer look at the time headway issue. Here we have a couple of figures that represent the time headways that were observed in the field with our traffic sensors. And we can see, again, based on guidance from the literature, time headway as well as heavy truck acceleration were worth exploring, and we'll look at the truck acceleration next. But with respect to time headway, the figure on the left shows the average time headway for passenger cars. And we can see most of those were between about 1 and 3 seconds. The figure on the right shows the time headway distribution for the heavy trucks. And we can see with the heavy trucks, most of them fall in about the 2 to 5 second range. So that shows that the time headway or gap that heavy trucks allow in front of them tends to be longer than what we see with passenger cars. Again, that kind of agrees with what we had expected. With the VISSIM 9 version, which is now a couple versions ago, but what we were using at the time the modeling occurred, headway could then be modeled as a distribution. Prior to that, it was a fixed or static value. In other words, implying that every single vehicle tends to keep the same gap or time headway ahead of them. And we know from our experience using the system that that's not necessarily true. So we did make use of that, what was at the time new functionality in VISSIM, to enter headway as distributions and separately for cars and heavy trucks, as we see here. We also explored heavy truck acceleration as well. And one motivating factor for that was the fact that VISSIM is developed in Germany and looking at using the European heavy truck fleet as its models. But the heavy trucks in Europe are generally smaller, shorter, lighter, and have more rapid acceleration capabilities as a result than the heavy truck fleet that we run here in the US. For example, the default heavy truck acceleration value in VISSIM is 8 feet per second squared. But prior research has shown with the US heavy truck fleet, again, larger vehicles, typically 2 to 3 feet per second squared is where most vehicles, heavy trucks capabilities acceleration-wise fall. So since this was one of the parameters that we varied in our calibration, we varied this in intervals of 0.2 of a second at a time. But again, honed into that 2 to 3 foot per second range, because not only do we know that to be more realistic of the traffic that we're modeling, in this case in Alabama, but also it was a tool to help improve the quality of the calibration. So let's move on to the topic of starting to do a little bit of work in exploring capacity stochastically or probabilistically. Typically, we view highway capacity in most any situation as deterministic. In other words, based on a certain set of traffic and roadway geometric characteristics, we've got equations that can produce a single value as here is the capacity on that facility for that given set of traffic and geometric conditions. Now, moving forward with the Highway Capacity Manual 6th edition that came out about 5 years ago, the freeway lane closure models for work zones took a big step forward. The equations got more complex. There were many independent or input variables that were examined to be able to produce what is still a static value for the estimated capacity of a freeway lane closure based on everything from roadway geometrics to the type of work activity or intensity of work to the number of lanes being closed and the configuration of those lanes, etc. So with the current edition of the Highway Capacity Manual, we're in a lot better shape than we had been before. However, some research developed over the last couple of decades or so has suggested that capacity is not really a fixed value, but varies across a little bit of a range at any given site. There's a bit of randomness there. And this is also what we saw in our field data from the site on I-59 and I-20, is that rather than there being a single value in terms of flow rate above which you could always count on a breakdown in a queue to occur and below which traffic would flow freely, that value was a bit of a moving target. So that further supported the notion that we need to explore looking at capacity as occurring across a range and ultimately as demand goes up, an increasing probability rather than just going from 0 to 100, but across a range, an increasing probability that a breakdown will actually occur. So the methodology that we used was based on some recent research performed for typical freeway sort of bottleneck situations, lane reductions, for example, and also at ramp metering locations using a method called Kaplan-Meier survival analysis. And to the best of our knowledge, this is the first time that this method was applied specifically to lane closures or freeway work zones. And it's supported by the data that were collected and the breakdown events that were observed at our study site. And here is a hook for potential usefulness to state DOTs or transportation agencies that might want to answer a question about what is the probability that a breakdown will occur, and then we have the subsequent queuing and safety risk for secondary or follow-on crashes? What's sort of the tolerance threshold that an agency would be willing to accept? So we took this sort of philosophy and developed a full experiment design across a range of conditions over which this could be explored. And that actually sets the stage for further exploration in a subsequent STRIDE research project that is still ongoing. And we executed within the scope of this project a pilot or test case. Simulation modeling was needed to produce a lot more breakdown events than were observed in the field so that we could be data rich enough to develop this model. And for this pilot or test case, it was just a specific lane closure side and a specific truck percentage value, but this can serve as the basis for a decision support tool for state DOTs once distributions are fitted. So here we're looking on the right at a figure that shows as the traffic volume of vehicles per hour per lane increases, based on what we saw at the site that we had data for, what's the probability that a breakdown will occur. So to kind of wrap up the work that was done at Auburn as part of the study, some of the lessons that we learned in model calibration, it's pretty important to look at your truck acceleration values. If we leave those with the default values in VISSIM, we are representing trucks being able to accelerate a lot more quickly than they actually can here in the US because of differences in the truck fleet. And that can lead to unrealistic results and also make the model more difficult to calibrate than if we go ahead and change the truck acceleration values to reflect the fleet that we have here in the US. Also looking at time headway values, we happen to have field data that captured that information. So we said, let's go ahead and use that. And let's represent those as a distribution rather than a static value, because that increases realism, as well as separate distributions for cars and trucks. As we saw a few moments ago, our field data supported that approach. And here's a table in the report that essentially shows all of the different parameters that were examined and changes to the default values. We've already hit on the most important ones, which were representing time headway with a distribution that's field observed and also changing the truck acceleration capabilities. But there were some other items that were explored as well. And then the last thing that we did in this research was execute a pilot test case that would be part of a much larger experiment as a decision support tool. And then our recommendations were to obviously study more sites. At this point, the research was based on one rural freeway site. At other rural freeway sites across the southeastern region that's covered by STRIDE, these sort of key values where we start seeing breakdowns occur might vary a little bit. Also looking at other configurations, such as a reduction from 3 to 2 lanes or from 3 to 1 lane. And then also further develop this decision support tool for the full experiment that was laid out in this particular study. And again, that's going to be addressed in a subsequent STRIDE research project. So this project sort of set the stage for that future work. Okay, so that wraps up my portion of the presentation. Again, I would like to thank STRIDE and the US DOT for supporting the research. I'd like to thank the Alabama DOT for being a stakeholder and providing input. And at this point, I think we can mention that if you have any questions, please enter those in the chat box. And there's also a link in the chat box to a survey that STRIDE likes to conduct with its webinars to get some feedback that might help shape future webinars. And then just to list some upcoming webinars that are representing STRIDE research. As was noted at the beginning of the hour, STRIDE's actually a consortium of 10 institutions across the southeastern US. So researchers are working at all these locations to see what we can do to improve mobility, since that's the key theme of STRIDE. So we can see, for example, the next webinar is 3 weeks from today, and it's an examination of work-zone driver behavior and how those data can be collected and then used to modify inputs in the VISSIM traffic simulation model. We can also see there are 2 more webinars listed there as well. And at this point, that closes the slide presentation that I have.
All right, that's great. Let me take over. This is Virginia again, so we'll give Rod a minute to catch his breath. So we have some great questions on the chat. I'm gonna take a few to get us started off, and then Rod can answer some of his questions. So one major question that I think is very interesting is the first one that reads, wouldn't calibration of bottleneck output flow be a more appropriate MOE to match? This is a great question. Actually, yes, we put a lot of effort in the calibration, but we calibrated the base model, not the model with the work zone. And the reason is that we did not have an appropriate location where we would have a 3-to-1 lane drop in our area where we could collect actual data. So this is one of the recommendations that we have for future work. So if we had the opportunity, then we would collect the actual data from a real lane closure of this type and then compare. But we did our best effort to at least have the same base model, the base model properly calibrated. But I think this is a very good question, and definitely, you know, worth considering for follow-up work. We had some other questions related to the design, for example, the taper lengths for used, as well as another question about the lengths of the work zones that we introduced. We used the MUTCD in order to guide us on the selection of these lengths. And another question about the VISSIM parameters. Are the VISSIM parameters used to model the behavior publicly available? Yes, all the decisions that we made after we calibrated the VISSIM parameters, those will be part of our report. Rod also mentioned some of his work with this, with VISSIM parameters, and those will be also available. So I will pass the mic to Rod. Maybe he would like to answer a couple of questions for his part, as we have only a limited time, and I'll be available for more questions later on.
Okay, thank you, Virginia, for that. I see that there have been a couple of questions that have come in related to the work that was conducted here at Auburn. One of those questions is, what are default critical or minimum gaps for late merge or early merge movements? And what is the average speed of merging vehicles for both conditions? So there's maybe two parts to that question. On the first part, there wasn't a matter of early merge or late merge, since the study, the portion of the research project that we conducted at Auburn, we actually collected traffic data in the field. In terms of how the traffic control devices and signage are set up, it, I think, essentially works as an early merge, but ultimately it's what the traffic out there chose to do. In terms of the average speed of merging vehicles, once traffic was in the lane closure, so immediately downstream of the taper, we had an average speed of about 51 miles per hour for passenger cars and about 48 miles per hour for the heavy trucks. So it was about 50 miles per hour composite. But of course, that's a function of a lot of things. It's a function of the intensity of the work, ultimately all the factors that influence how drivers choose to select their speeds. So that's what the field data showed us. Even though the field data showed us that the upstream sensors average speeds were generally in the 70 to 80 mile per hour range. And the posted speed limit on this facility is 70 miles per hour. And then near the work zone, it was reduced to 60 miles per hour for the purposes of the work. And that's interesting that the posted speed limit through the work zone was 60 miles per hour. Yet once we got into the lane closure, the average speed was actually about 50. And that again reflects all the sort of things that the driver feels sort of compressing their space, governing the speeds that they select. That would be my take on it. Another question was, what type of detectors were being used to collect the data, which can give the vehicle length information. They are actually magnetic detectors that were placed in the roadway. They were manufactured by MH Corbin. The NC350 traffic analyzer, I believe, is the name of it. And so what we actually did was drill holes in the pavement and drop those sensors on the pavement, and then place a protective cover with several screws around the sensor to hold it in place. But it's essentially a magnetic detection technology that would note, as a function of the time that the sensor was sort of occupied, the vehicle length is actually estimated. It's not an actual measurement. It's an estimated vehicle length based on the data that we're collecting. So there's a couple of the key questions that I think were fielded toward the portion of the work that I did, or that was conducted here.
All right, let me take one more before we wrap up from that first portion, and it reads, what was the vehicle composition percent track and posted speed? And also it says sensitivity analysis of these effects would be beneficial. Yes, the vehicle composition was 10% tracks, and the posted speed limit on the freeway was 60 miles per hour, and on the ramps 45. And I would definitely agree that the sensitivity analysis would be beneficial. And we did acknowledge that on the continuation of this work. We did additional work with the 3-to-2 lane closure scenario, where sensitivity analysis was performed for track percentages and different behaviors of drivers and so on. So I thank you for this comment, and we hope that our report will be available after the end of the summer. So you are welcome to check it out, and we welcome any feedback that you may have on that as well. So Undine, I don't know if you would like to have any closing remarks, or Rod, I'll pass the mic to you guys.
Yes, thank you both so very much for today's talk. If you haven't yet completed our survey, we do ask that you complete that so we can better provide better webinars for you in the future. The link is in the chat box. And if there were any questions that we weren't able to answer today, we'll try to provide those in a follow-up email with a copy of the recording of today's webinar. Thank you so much, and we hope you'll join us for future webinars.